Okay, folks, so we're going to sketch the graph of a function f such that f prime of x is negative for all x, and the rate of change of the function is increasing. Okay, all three graphs in front of us here are the graphs of functions with a negative slope. I don't know why that's skinny right there. This first one, that slope is always the same. So the rate of change is constant. On the next one, we have a rate of change that goes from, say, negative, our slope, oh gosh, I need to not just point to it, I need to point out what I'm talking about. So right around here, we've got like a slope of maybe -5. I don't know, some like positive integer. But over here, we have a slope of maybe -1/5. So that's a possibility because our numbers are our slopes are increasing from -5 to -1/5. On this last one, we're going from a slope of about -1/5 to about -5. So things are a bit fuzzy here, so I'm trying very hard to think through my explanations before I say them out loud. It says that the rate of change of the function is increasing, which means it's getting less negative. So our appropriate answer is this middle one. But I want to talk a little bit more because what we have happening here in the middle is that your function is decreasing at a decreasing rate. But over on the right, this far right one, it's decreasing at an increasing rate. And you're not going to see the importance of that right away. But this is a very important distinction. It specifically says that the rate of change of the function is increasing. If the rate of change of the function is increasing, we are definitely looking at the middle one because our slopes are getting closer, closer to 0, but that doesn't translate well to what you're going to see in the future. Your rates are getting I want to say more positive. That's not true. Your slopes are getting bigger. Yeah, bigger. Because -1/5 is a bigger number than -5. Whew, that was hard for me to verbalize. Okay, moving along. The situation on the right is going to become important later in the course. And you're going to have to carefully think through what seems like something trivial and may seem confusing today. And you're going to have to do that now to be ready for what's coming. Okay, next up, we're in the fun stuff. Find A and B so that f is differentiable everywhere. In order for something to be differentiable, it must be continuous and differentiable. So in order for it to be continuous and differentiable everywhere, it must be continuous and differentiable at the point at that piecewise point. I don't know what that point is called. So, we need, in order for it to be continuous, we need to show that the left and right hand limits agree. We also need to show that the function exists at that point. And we need to prove that the limit also equals the function at that point. So we'll do that part first. Okay, we have a problem. We have too many letters and not enough numbers. But this is Calc 1, not your senior year of a math degree, so you know that there is a solution in here somewhere. In order for it to be differentiable everywhere, we have to look at the derivative from the left and from the right. So we are going to examine that quickly and figure out what values of A and B would make the derivatives match on both sides. Okay, at this point, you have a system of two equations and two unknowns. You might not be able to see it yet, but you will in a second. We can set these two equal to each other when x equals 2, and these two equal to each other when x equals 2, and it allows you to solve for a and b. So here your function is differentiable when b equals 4a. Now we're going to go back into the definition of continuity and figure out what that means up there. So in order for the function to be continuous, the limit from the right has to equal the limit from the left. So let's find those values. So we can see that in order for it to be continuous, 2b minus 3 must equal 4a plus 1. Well, we already know what b is. So let's go ahead and use that information and replace b with 4a to solve for a. Okay, just to be clear here, this step right here is just me subtracting 4a and adding 3 to both sides. Okay, so we go ahead and solve for a and b, and then, especially if you're me, you go back up and you ask yourself if you actually answered the question, and the question was simply asking for values for a and b, and I have done that. Yay, first time in a long time. Next page. Ooh, we've got a diver jumping from a diving board. Exciting times. You definitely need to graph this on your graphing calculator before we do anything else. So do that quickly. Hey y'all, it's me. I just ended up, life kind of got in the way, so it's been 4 hours since I talked. I think I told you to graph this on your calculator, but haha, that's funny. Because you can't graph that because you've got two constants there that you need to solve for. So, when does, oh no, that's not true. Oh my gosh, I can't read. Okay, I'm going to read this out loud because clearly that is necesito. At time t equals 0, diver jumps from a diving board that is, by the way, I don't speak Spanish. Diver jumps from a diving board that is 32 feet above the water with an initial velocity of 16 feet per second. Use the position function s of t equals negative 16t squared plus v naught t plus s naught, where v naught is the initial velocity and s naught is the initial position. Well, you have this initial position right up here, and you have the initial velocity right here. I don't know where that song is coming from. I don't know where anything comes from in my brain. So when does the diver hit the water? Well, the diver will hit the water when that diver's position is 0. So we're going to go ahead and look at this. I'm going to graph it because I have been hanging out with high schoolers for too long, so I need to see these things. So here's our equation and our graph. Notice that I cropped the graph. I hope, if you did not, you should graph it yourself on your calculator. So when you look at that graph, this green line actually extends down over here, correct? But we don't care about what happens before the dude jumps, or the girl, or the rabbit jumps from the diving board. We care what happens after that jump, because the rest isn't actually real. We also don't care what happens when the diver goes underwater. So I cut it off. This right here is the x-axis. You can't tell really, but unless you graphed it yourself, which hopefully you did. If you did not graph it, please graph it on your calculator. Push pause, push pause, push pause. So we want to know when it hits the water. Well, if we look at that graph, we see that it hits the water when y is 0 and x is 2, but you actually have to do the math because this is math class. So we factor and we solve, and we get that t, either the diver hits the water at t equals 2, I want to say seconds, yes, seconds, or at t equals -1 seconds. Well, again, that t equals -1, that is meaningless. That is meaningless because we don't care what happens before he jumped off the diving board. So t equals 2 is our appropriate answer, or the diver will hit the water at time t equals 2 seconds. Once we've discovered that, we need to find the instantaneous velocity when t equals 1 second. Well, instantaneous velocity is determined by the first derivative. So we go ahead and find the first derivative of the position function, and there was quite a discussion one year when I graded the AP exam, and I really want to make this very, very clear. In the past, we used to refer to velocity in terms of v of t with no context given. As of 2018, it became very clear that you must indicate that v of t also equals the derivative of the position function. So if you are going to refer to this instantaneous velocity without describing its relationship to the position function, you will not receive any points. Because whenever you're taking a test, whether it is for your professor or it is for the AP exam people, it is about communicating your understanding. It is not enough to understand the math. You have to be able to communicate that you understand your math. Once you've made that relationship clear between the derivative of the position function and the velocity function, then you can go ahead and refer to it as the velocity function. No need to restate that, that relationship anymore. So we're going to go ahead and find the velocity at 1 second, and the velocity at 1 second is -16 feet per second. And units are important. Most of you have learned that because most of you have taken physics and or science classes of some sort. So you also want to write that out as the instantaneous velocity at t equals 1 second is negative 16 feet per second. Now all we have left to do is the average velocity, which is just algebra slope. So we're going to find s of 2 minus s of 1 all over 2 minus 1. Put your numbers into the algebra slope, or y1 minus y2 over x1 minus x2, and you get negative 32 feet per second. Okay. The graph of a position function is shown. Sketch the velocity function on the interval from 0 to 9. Okay, this first bit from 0 to 4, had to count, that all has a slope of 3/2. So from 0 to 4, our velocity function, or our slope, is 3/2. From 4 to 7, our velocity is 0. 4, 5, 6, I don't know why it's so hard for me to count right now. Everything's hard for me when I'm trying to be perfect. Okay, the next one, from 7 to 9, our slope is 1/2. So our velocity function looks like that. Notice that our function is, or our velocity function is undefined at our corners. That also should bring you back to remember that the fact that a function is not differentiable at corners. Okie dokie. The assignment listed here will probably not be your assignment this evening, or I'm sorry, during class. So pay attention to blend, not what is listed here.